I'm not going to be standing up here, I don't think, because I'm a wanderer while I speak, so I'm going to be going back and forth, and also I want to see the slides. Anyway, I am thrilled to be here. When Barbara first contacted me about speaking at the Kaplan Institute, I had no idea what it was. By the way, I live in San Diego. I was born in Oak Park, though. So just, I lived in Arlington Heights for the first few years of my life. But I'm a New Englander at heart because I grew up, my whole family clan is from the Boston area. So yes, I'm a Patriots fan and all that. So don't hold that against me, at least not yet. But anyway, it's a real pleasure for me to be here. I love what the Kaplan Institute is doing with integrating multiple disciplines in the education process. I love all that. One of the reasons why I'm doing this talk is because over my 30 plus years of doing what's now called AI or data science, or before that predictive modeling, before that data mining, before that pattern recognition, and yes, I'm old enough to predate all of those labels, I've done the same thing my whole career, essentially, which is kind of machine learning-ish, neural network-ish problem solving. Because I'm a math guy, computational math undergrad. I was a double E minor and a music minor, just one course short of a music minor, to be honest. And I got a master's in applied math. I was interested in control systems. I love differential equations. I just thought they were the coolest stuff. But my first job, I was with a small company of 5 people, and that small company is a 50-year-old aeronautical engineer and a bunch of young guys working with them. I was introduced to statistical learning and just fell in love with it. In fact, everyone in that company went on to form consulting companies or software companies doing statistical learning. One of them is a name that you may see in the data mining or data science space named John Elder. John and I are great friends. We've worked together. We've competed against each other and through the years. Fascinating space. But now the cool thing is after spending my whole career as a geek where nobody cared about what I did, I was in the back room just doing all my algorithm stuff, but now people care. So the 2012 Harvard Business Review, the sexiest job of the 21st century is data science. I mean, how cool is that, right? Now we're finally sexy, right? And we can finally do something that other people care about. So anyway, this talk is about things that you probably haven't talked about that much, but over my years as a consultant, and I was an independent consultant for 15 years, now I have a company, have a startup company that's now an early stage company with 80 employees doing personalization and marketing primarily for retail. And my work was the analytics back end and backbone for what we do. So here are some things that we do. Here's the agenda. 5 things that you probably weren't taught. Number 1, you are not going to be understood. Number 2, what you predict matters much more than how you predict it. Data is bad, data prep matters, and machine learning algorithms optimize the wrong things. So I've already spoken with Mustafa about a lot of these issues, and we have a lot of synergy and agreement about these kinds of things. Okay, so what do I mean by these things? Let's see if this... Did I do something wrong? This is not working. So I may need somebody to manually advance. Okay. So the first thing I'm going to talk about this. Has anybody here seen CrispDM before? Nobody. So that means I get to introduce you. Oh, I saw one hand kind of go up? Yeah, okay. So this is not the only way to describe analytics and how we do analytics, but this is one way that's in a PDF document that's like 50 or 60 pages. So when you get your job and you're working for a company and your boss doesn't know anything about analytics, and you tell the boss, this is the kind of stuff I do, well, you can give them CrispDM, and it'll describe in block diagram form because, as an engineer, or at least a minor in engineering, all the world can be described in block diagrams, right? So block diagrams are really cool things. So that's kind of block diagram-ish. I'm going to focus a lot of my attention on the first stage, business understanding, how to define the problem you're trying to solve with analytics, okay? That is where almost all failures in analytics projects occur. It's not the technology, it's not the models that you build as a data scientist or an AI practitioner, it's how the problem is set up. That's where things fail. Okay. Number 2, data understanding, getting a lay of the landscape for data, then preparing data, building models, evaluating the models, and then finally deploying the models. Those are the different steps. Now, one of the things, if we can go to the next slide, let me try this one more time. I'm going to see if it goes, no, this is not working. Or it's really slow. So go back one again. So this applies to any analytics discipline, so that's why I changed CRISP-DM to CRISP-DS and call it data science, because I'm labeled as a data scientist now. I have to say, for years I rebelled. I used to say, on my Twitter feed, I used to say, I'm frequently called a data scientist, but prefer not to be, because I really didn't like the term, but I finally succumbed, and in the end, I don't care what people call me. As long as you give me data and I can build models, I don't care what you call me. Okay, next slide. And we'll have to do this for a little while. Number 1, you won't be understood, and you're not going to understand the domain experts in your business. Okay, whatever company you're working with, they're not going to understand you. You're going to talk past each other. So go to the next slide. And it's kind of like this. You are the machine, or you're representing the machine, or you are the one who is going to explain what the machine can do to the flesh of the business. And we need that kind of communication. Go ahead, next slide. And no matter how loud you shout about what the math is doing, no matter how clearly you think you're describing, of course decision trees will do this kind of thing. Of course there's going to be this kind of bias. We need to incorporate misclassification costs. We need to do all those things. They're not going to have a clue what you're talking about. They're not going to understand how and why you have the problems you have with the data. They're not going to understand why, when you have missing values in your data set, that's going to kill your neural network unless you find a way to fix it. Because when humans look at data, they look at let's say they're looking at a spreadsheet. They're that technical that they're going to look at that spreadsheet and they see a value there that is just not right. It's obviously not right. Like the total assets of a corporation is $10 trillion, which I actually saw when I was building models for a tax agency once. $10 trillion. When we look at that, we just go, of course, that's wrong. An algorithm has no common sense. It has no idea. It believes everything you tell it. And the only thing you tell it is in the data. The data has to be completely correct. Okay. Oh, perfect. Thank you so much. Let's see what's next. Okay, so one of the funniest Oxford-style debates I ever saw was at a Strata conference, 2012. And I didn't go, but this was online. It was the only thing I could see online about the conference. So I thought, okay, I'll watch this. It was a debate, and this is in San Francisco, so keep that in mind. The question is this: if you've got a startup company, who should your first hire be? Should it be a domain expert, or should it be a data scientist? Okay, so think about that for a minute. Who should your first hire be? Now, look, this is a Strata conference in San Francisco. We know what the answer is going to be, right? And how that's going to land. But I was watching this debate, and this video that's on the screen had an interview with a purchaser. I'm not going to name her now. I'm happy to name her somewhere else because I talked to her afterwards about my comments. She has won multiple competitions, KDD Cup competitions, which the analogous competition today are Kaggle competitions. So she won a whole bunch of these. Super smart, super good at building machine learning models. So she's building these models. She won them all, and she said, look, you do some Google searching, use some good principled approaches to how you build the models, and you'll succeed. And I was screaming at the screen. And this is what I was screaming at the screen. I told her later when I was speaking at a conference with her, and I said, this is what I said. She goes, oh, I agree with you. So this is what I was screaming. When you do a competition, you go, has anybody here done a Kaggle competition before? You can be bold. Raise your hands. I strongly recommend, if you want to get into data science and AI, try your hand at a Kaggle competition. It's a really good way to kind of cut your teeth on building models, and there's a community around Kaggle competitions that will help you. What do they give you when you do a Kaggle competition? They give you a data set. They give you the target variable, the column of the data you're going to predict. They give you the metric to use to decide whether a model is a good one or not. Are you using the rock area under the curve, or using some kind of classification accuracy? They give you all that. I was screaming, by the time you get that, you're 80% of the way there. If you were starting from scratch as a data scientist with a business, how would you know what target variable to use, what column to form in the data that's going to identify what you're predicting? When I was predicting for the Defense Finance and Accounting Service what invoice fraud was, we had to have a column in the data that said this is representing in our data which invoices are fraudulent and which invoices are not fraudulent. That labels all the algorithms have to tell them what the answer is. That's supervised learning. That's all they've got. If that's not represented properly, if that's not represented the way the business is making a decision, your models are going to predict the wrong thing. That's hard. You need the domain expert to help you with that. A data scientist is not going to jump into a new company and understand how to do that. It needs to be a collaborative effort. So the way Mark Driscoll, who moderated the debate, said it, there we go. It's when a good question is posed, it's much easier for machine learning to succeed. So that's the Captain Obvious moment of the morning or the afternoon. If you pose a good problem, if you pose a good target variable, you're more likely to succeed. So I usually recommend something like this. I call this the three-legged stool of successful analytics. You need 3 people in the room when you're defining the problem to solve. You need the domain expert, the one who understands the business, understands the decisions or the process that the algorithms are going to help define and help improve. You need the data people, the people who know where the data is, what the data means, how to access the data. Because oftentimes the data scientist doesn't know where all the data is hidden. And you need the data scientist to understand how to contextualize the data. If any one of those are missing, if you're missing the domain experts, your data people will build fantastic models that solve irrelevant problems, right? If the domain experts are there, but the data scientists are there, they'll define a problem that's impossible to solve because the data doesn't exist to solve that kind of problem. You need them all there. Okay, next slide. What you predict matters more than how you predict it. And let's go next. I think we're going to have to do it manually. So I already defined what the target variable means. The target variable in predictive modeling, think of an Excel spreadsheet. It's that column in the data that incorporates what the algorithms are going to try to predict. And it could be classification of 1, 0, or yes, no, or something like that. Or it could be a continuous value. So when you're trying to predict that, let me give you one example. So when I was working for a tax agency, they wanted to identify, actually I think I can say this publicly because I'm being recorded, so I'm being very careful about what I say and what I don't say. I worked for the IRS for 10 years. Now, I didn't see any of your tax returns. I only worked trying to predict noncompliance for companies with more than $10 million in total assets. So if you've got more than $10 million in total assets and you're an S-Corp, then I probably saw you at some point, but I assume most of you are not. But anyway, so when we're doing this, the question is, what does non-compliance mean? What will the algorithm try to predict? And you can do that in a lot of different ways. One way to do it is say, the obvious thing is, oh, let's see what auditors did. Auditors looked at tax returns. Some of those tax returns, they say, oh, the company owed money. That's a 1. That's non-compliance. Here's another tax return. They were audited. They didn't owe money. That's a 0. So you could do it that way, but there's a problem with that. The problem is this. Not every tax return that was not audited or that was given a 0, it's not always the case where that's reflecting what the true risk of the return is. Sometimes what would happen is the statute of limitations is running out after 3 years. And after 3, the statute of limitations is coming up, and the auditor just says, I don't have time to look at this. I'm closing it. Or there's another one that's super complex. The auditor's saying, there's no way I'm going to be able to finish auditing this return in 3 years. That's a 0. That's not representing the risk. So we had to come up with another way to identify what we're trying to predict. You need the domain experts to help you with that. Okay? So be very, very, very careful what you're trying to predict. It has to incorporate fully what the machine learning algorithms are trying to call a 1 or call a 0. And here's an example. That's the target variable. This is the Titanic data. If you ever go to Kaggle, the perpetual competition that's up there all the time is the Titanic data. And the data looks something like this. And here are the first, 10 or 15 records of that data. And you see who survived, 1 or 0. In this case, that's probably a good indication of who actually survived. That's probably a pretty clear predictor. You've got things like their age, what class of service they were, whether they're male or female. And I have to say, sometimes when I look at this, it makes me really sad because there are actual names here. And those are real people who really died on the Titanic. When you see that one family where the only one who survived was that infant, and everyone else in the family died. So usually when I teach this data, I scroll down. I say, I don't want to see that particular case. But this is the idea. Here's what we're trying to predict, and then the rest of the data are the things that are trying to predict that. And so that means we have to define, when we're looking at this from the perspective of the business, we have to translate that into what our objectives are, our analytic objectives are. And that translation into the analytics objective means defining what we're trying to predict. Are we trying to predict fraud? Are we trying to predict some other kind of risk? Are we trying to predict the dollar value of fraud? Is that a more valuable thing to predict? The business will help us understand that. Okay, so that has to take place up front. And I think I'm going to skip this slide. That's just highlighting those things. Let me give you 3 examples. I've already talked about taxpayer noncompliance. Customer churn. The first customer churn attrition model that I was asked to start walking through with a company, the question I asked was this: what do you mean by churn? How do you define churn? Well, it's when a customer leaves us. And this is for a credit card company. It's when the customer leaves. Is that really what you want to know? Or is it something like this? A customer whose regular use of the credit card was $2,000 a month, and then for the next 3 months, it's less than $100. Isn't that churn? Couldn't that be defined as churn? But that's a different target variable. That's getting at a different characteristic of the customer. And those are the questions you've got to work through. And then the next question is this: once you identify churn, how far in the future do you have to predict churn? How far in the future? You need to predict far enough in the future so that you can do something about it. If I'm predicting you're going to churn tomorrow from a credit card perspective, you're lost. There's nothing you can do about that. That's great. I can tell you that you're going to churn tomorrow, but the company can't recover you. It needs to be far enough in the future, maybe 1 month, 2 months, 3 months in the future. All that has to be baked into that target variable. Okay, next. Data is bad. Really, really bad. Everyone who tells you that their data is clean, and I'll tell you, I was a consultant for 15 years, and I'd go into a company and I'd ask them about their data, and they'd say, yeah, our data is really good, Dean, really clean, and they're all liars. No data is particularly good. No data is clean. And one reason why that happens is, in the data lake, they say it's all pristine, but the real truth of the matter is there is just junk everywhere. And junk that even if they have a strong BI department, business intelligence department, that summarizes reports in the data, what do those reports do? Those reports will smooth over data problems to give you the gist of what's going on. Oftentimes, when we're building predictive models, we're like Lewis and Clark. We're the first people as data scientists to ever look at granular levels of data. We're the first person to ever really explore the data in detail. And for us, every value matters. If there's a bad value, it can have a significant effect on the models. So we care about looking at the data. So when we're doing data understanding and data preparation, here is a data set which is a marketing data set for a nonprofit. They're trying to recover lapsed donors. And this is what I call a data audit that just summarizes statistical summaries of, in this case, it's the continuous values. And I know you can't see that, so I'm going to highlight things. And we need to ask questions like this. For age, the mean age, and this value that I've highlighted is the mean, 61.6 years old. First question, does it make sense? And in this case, it did. And then after you do that, then the next slide, the minimum age. It's 1 year old. Okay, so now thought experiment. You've got 1-year-old donors in your data. What does that mean? Do you have 1-year-olds writing checks, swiping credit cards, doing something, of course, no. That's not the case. So what does that mean? Because the algorithms, again, they don't have common sense. The algorithms see that, they think, oh, it's a 1-year-old. Are 1-year-olds more likely or less likely to be recoverable lapse donors? And that's not what we want to communicate to the algorithms. We want to communicate accurate information. So from our standpoint, whatever the reason is, whether that is an encoding of missing values, or if that's a grandparent donating on behalf of their grandchild, we need to represent that in some form in the data. In this case, if we're going to make decisions on the age of a donor, we need the age of the donor there, and if we don't have the age of the donor, it's a missing value, and we've got to do something else with it. Okay, and then of course, there are things like, let me go one more, missing values. So be very, very careful about the data. Spend a lot of time looking at your data. One of the ways I hear people describe this process, they'll say data preparation, looking at the data and fixing data problems is 2/3 or 3/4 or 80% of the time you spend before you build your first model. And that's probably about right, because all the data is going to have problems, and it takes a while to figure it out. I also mentioned to Mustafa earlier that how many books on data preparation have you ever seen? Has anybody read a book on data preparation before that's just dedicated to data preparation? I know of one, and it's by Dorian Pyle, called Data Preparation for Data Mining. It was published in 1999. I actually have it, you can get it for free now, and it actually is pretty good. But the reason why I think they don't write books like this is there are so many ways data can go wrong. There are so many ways that people mess with data. I tell the database people, the database architects, don't fix the data for me, because you're going to fix it wrong. The way I want to fix it, and we don't have time to talk about that here, but in my book, I've got a whole chapter in data preparation and how the way you fix data depends on the algorithm you use. And so there's a dependence there. So don't fix my data, let me do it. Okay. This is really interesting. Anthony Goldblum is the CEO of Kaggle. I met him, I don't know, like 10 years ago. And just to show, I'm not a good marketing guy, and I'm also not, I'm entrepreneurial, and we could talk about startup companies and being entrepreneurial. I'm not naturally wired that way, and he is. When he told me about this idea, he said, Dean, I've got this idea. I'm going to have data competitions, and people are going to provide data. And he told me about the whole business model. I'm like, I don't know. That doesn't seem like it's going to work. Yeah, like, what do I know? It's been very successful. Kaggle's been a great company. And there are two things here that were very interesting. The first post on the left is from the Kaggle blog, talking about how important feature engineering is. On the right is from a Quora post. How do you win Kaggle competitions? Feature engineering is tremendously important. What is feature engineering? It's taking the raw data, those raw columns of the data, and creating new versions of the variables or new versions of interactions between the variables. So let me give you an example of this. What is an interaction? Here is an example where you've got two variables, placebo and how much and the strength of the drug that someone was taking, and then you've got a measure of their pain. And there is a strong interaction between males and females with the placebos or how much of the medication they're taking. So if you're looking at the overall trend versus the conditioned statistic, conditioning on sex, then you get a different story. Let me show you this. This is even more plain. Here is a blob of data, and if you drew the trend, I know it's very noisy, the trend is a negative correlation between those two variables. However, if you conditioned on another variable, both of the sections are positively correlated. This is actually a phenomenon that's well known and well understood. It's called Simpson's paradox, which is sometimes the overall statistic trend is completely reversed from the trend from subgroups. And there's a real cool kind of Wikipedia post on this with gender bias in graduate schools at UC Berkeley and how women were accepted at a lower rate overall, but in almost every department, women were accepted at a higher rate. So how can that happen? Well, it's an interaction effect. It turns out that women applied to the more difficult schools to get into, the different departments to get into. So the aggregate statistic was suppressed because the subgroups were not the same size. So things like that are very important for us to think about. Interactions can uncover those kinds of trends. Fifth point, machine learning algorithms almost always optimize the wrong thing. This, I was telling Mustafa earlier, I almost left data science in the early 2000s because of this problem. And I almost went to optimization. Because in my graduate work, I was doing optimal control, variational calculus, which was super fun. I got to guide missiles with it in my early career. It's really, mathematically is a lot of fun to do. But I decided against it for some reasons that I'll bring up in a moment. So here is a listing of the metrics that were most commonly used in machine learning. Let's skip one more slide. Let's keep going. Here we go. Mean squared error. What algorithms use mean squared error? Of course, regression uses mean squared error. Any algorithm that uses Euclidean distance, like k-nearest neighbor, k-means clustering, or even algorithms like PCA, principal component analysis, they're all squared error based. Why does linear regression use squared error? Is it because there's something inherently better about squaring errors? That it just communicates to the business so much more effectively to think in terms of squares of errors? And the answer is no. The reason why these algorithms are squared error algorithms is because the math is easier. The math is a lot easier. Linear regression is a closed form solution because the math is easy. So that does not necessarily mean that building a linear regression model will map to what your business wants to do. What are some other algorithms that people do? Decision trees with information gain and the Gini index. Very cool. So this, let me go back one if I can. Okay. Here is just for the Gini index. That's a formula showing you how you calculate Gini, where P is the proportion of ones on the left side of the split, and you also have the proportion of ones on the right side of the split. And you just square the proportions and sum them up. That's all Gini does. Information gain does something very similar, and you can see it maximizes at the 0.5 mark. So that's very cool. Now, when you go to your, like when I'm building purchase propensity models for, let's say, for Hilton, that I'll do, and I tell them, you know, the Gini index was 0.169, super cool. Will they care? And the answer is no. They're not going to care. They won't, first of all, they won't know what it means. Second of all, even if they knew what it meant, they wouldn't care. What do they want to know? How much money am I going to make from this model? What is the ROI? So that's what I want us to think about. How do we map what these algorithms do to the data mining success criteria? So you're building a linear regression model, squaring errors. How does that map to what the business cares about? That's how we want to reflect what the models are actually doing. So let me give you a quick example of that, if I can get through all the build. I'm going to skip that for now. Just out of time. One of the ways predictive modelers do this a lot is they use what I call rank-ordered approaches. Rank-ordered approaches. So mean squared error, I call a batch error metric. It uses every single record in your data set. You compute the squares of the errors, you average them. That's mean squared error. Another way you could accomplish that is by using rank-ordered approaches. Let's say you're building my purchase propensity model that I'm building for Hilton. Every record, what the logistic regression model predicts is a probability. I could rank it from highest probability to lowest probability. So first thing you do is you sort, and then you compute some metric based upon that sorted list. And that's what all of these algorithms are doing. Raw curves, lift, gains charts. What proportion of the people who responded are picked up as we sort the probability from high to low? And if it's high, let me go back one. Like here, 20% of the way, I'm getting 20% of the responders at 10% of the depth. So I'm twice as likely with that model to pick up a responder than a random selection. And frankly, that diagonal line for gain or a diagonal line for rock is the random line. Whenever I'm doing consulting, if I've got to compare myself to a random, I am loving life because I can always do better than random. Even if the joke is, even if my model does worse than random, just do the opposite of what the model says, and now I'm automatically better than random, right? So you always win when you're comparing to random. So I like that. But anyway, rank ordered approaches. So it's a different mentality. One of the things you could do, what if you sorted your data, like my lapsed donor model? How much money am I going to make when I contact a lapsed donor? Or how much money am I going to bring to the IRS's coffers if I rank order by most likely to be suspicious or non-compliant to least likely? And you can calculate that by how much will I recover from this record and this record and this record, how much does it cost me to investigate each one of these, and I can compute a profit as I go down this list. And when you create that profit, you can generate something that looks like this profit chart. Where in this case, for the lapsed donors, at the 70% depth, the model is going to generate about 7.1K per 100,000 donors. That's something the business can take home and know what they're going to do with, okay? More so than the mean squared error or something like the misclassification rate or something like that. So think about work with the business and understanding what metric they care about, and then when you report how good the models are, pick the metric that works the best. Now, one of the reasons why this is critically important, I don't know if I've got a slide here on it. Yeah, this is the slide. Here is a data set from a competition more than 10 years ago. They were using the rock area under the curve as the metric, and that's this first column there, 70.01% versus 69.99%. As a sidelight, I feel bad for the 69.99% folks, because that's almost certainly within the margin of error. If you looked at the uncertainty of the predictions, they lost on a coin flip, essentially. So that's really too bad, but they still lost. But those are the top two performing models. What if we used a different metric? Rather than rank ordering all the data and computing this one metric, what if we said, look at the top 10% of scores and compute the lift, the model lift of the top 10%. That's what this second column, the far right, and I apologize to everyone over there, it's at the far right. And look at this, like the 20th best rock area of the curve model was the second best with top decile. I've done this kind of experiment with lots of error metrics, and there's one time I built thousands of models, and I did a Spearman rank correlation on those two scores. They were uncorrelated. Which metric you use will dictate which model you select, which is why it's so critically important to pick the right metric for the business so the business has the best model available for them to use. Okay, I think that is at the end of my slides. I will close it off here, and Howard, if we want to do any questions. And I'm happy to answer any question about anything here, about consulting, about entrepreneurship, or anything like that.
So you mentioned your company, and a lot of folks in the audience are interested in thinking about being an entrepreneur as a career, starting a company, whatever. And, you know, a lot of them have spent a great deal of time thinking about how that happens and how much research and everything they're doing. Tell us how your company got started.
So I worked for small companies and large companies, mostly small companies early in my career. And then about 10 years in, I got sick of being pulled off building predictive models and being pulled into something else because they didn't have enough work to do building predictive models. So like one company I was doing sensor redesign. Like I'm not a physicist, I was not particularly interested in that. So finally I decided to go out on my own and just do predictive modeling. What helped me was the first 3 clients I had were former employers. So rule number 1, don't burn bridges. Keep a good relationship with companies you've worked with. And usually when people come up and say, Dean, I want to be an independent consultant, how do I get started? The first thing I usually say is get a job with a company, work your tail off, learn that business, understand what matters most to decision makers. Because as an independent consultant, you've got to sell. I said I'm a bad marketer, but if you undersell and overdeliver, you will succeed. So understand what they want, build what they want, and do better than what they expected could happen. So it took a while for me to build up my own portfolio of consultants, but my first several clients were former employers, and that helped me get started. With Smarter HQ, so I did that for 15 years. And read voraciously, that's the word I want. Read a lot. I was reading all the time. Journals, popular articles, trying to understand how people think about data and how to connect analytics to their particular domain. So if I was doing a problem with like tax fraud, I would start reading about tax codes and tax fraud, look at the models that were already in production, understand how they built them, so that I could leverage the existing knowledge base available. Smarter HQ, which is a bigger company, because my consulting company was just me and 1099 employees every once in a while. But I did it because I didn't want the headaches of employees, because, employees are a lot of work. So this was a lot easier for me. But Smarter HQ now has 80 people, and that started in partnership with somebody else, with the other co-founder. We met at a conference. We started talking. I met at an analytics conference. We started talking, enjoyed the conversation. I canceled my flight. We kept talking, and we just started building infrastructure on the side until we had enough built before we could go live and go full-time.
This is somebody you didn't know before.
I had no idea who he was before. We'd met for the first time at this conference. In fact, my wife, who is really, she's got great advice. I love talking to her about any kind of business decisions. She's like, who is this guy? I said, no, he's right. What do you know about him? Do you know anything about, no, I really don't, but I think it's a really good idea. And he seems like a good guy, and he is a good guy. In fact, he's not with the company anymore because he wanted to move much faster than the company could move. He's really entrepreneurial. And I was the one who was just trying to bring, what I spent most of my time doing, in full honesty, he had ideas in his head, and I was trying to put some analytic teeth into his ideas. He said, I think we could do this with marketing campaigns. Well, I defined the data, defined what the metrics were, and he was like an artist. Like you think of an impressionist painting, where when you look at it from a distance, it all makes sense. But when you get up close to it, it just looks like garbage. You can't see anything. It only looks good from a distance. I had to deal with what it looks like up close so that when you look back from a distance, it all made sense, right? So I had to ask him very specific questions. We would have sessions that would last all day trying to answer one small metric. What do we want to use to, say, summarize what the value of a product interaction is on the website? And we'd argue all day long about it, going back and forth. But that helped us define something that was really useful.
So talk about, you talked about making sure that the data that you're deriving matches what the company really cares about. I would call that eventually storytelling. And talk about how important it is in your career, in your industry, to learn the communication skills and how big a role that plays over and above just the technical skills.
As a consultant, the data storytelling part is critical. If you can't tell the story, spin the tale, and I don't mean that as a pejorative, but letting the data speak, as people say, which I don't really like that term, but a lot of people say, I want the data to speak. We were joking about that earlier. The problem is, most of the time with business executives, they want the data to speak as long as it says what they think it should say, right? So they want it to speak their language and not what it's really saying. So how important is it? It is critically important, especially as a consultant or as the person who's responsible for an analytics group. You have to translate the geekery that you talk about within your analytics team into a language that the business execs can understand and make them feel confident that you're doing the right thing. We're having this conversation too. I would rather, any day of the week, build a model that was understood by the stakeholder, the business stakeholder, the project manager, that was 10% worse in accuracy if they could understand it and believe it, then give them the best possible model that was opaque and couldn't be understood. At least for most execs.
Because they can't use it, right? If they don't
Because they don't
understand
believe it. And if they don't believe it, they won't use it.
Right.
So one of the early IRS models that we built was a decision tree, and it had some splits in the decision tree that you talk to subject matter experts, auditors, and they said that makes no sense whatsoever. And once they say that, the model sunk. They won't believe anything it does, even if its accuracy is really good. So one of the things we'd do is we'd show models to people who were the subject matter experts, and when they said this doesn't make sense, we'd look at that variable, see if there's a surrogate for that variable that is matching close to what they believed should be the case, and then we could rebuild a model that made more sense for them.
Okay. Where are you on the the spectrum of whether whether machine learning is getting smarter or just faster with better data sets?
I don't think machine learning is getting any smarter. The math is the same. You know, it's the same.
So what's the path for improvement?
More data,
Better
more
data.
context, and ultimately better data. And more data hopefully is better data, but it's not necessarily better, just having more. But more sources of data helps because it gives more context to the entity that you're trying to predict, and better infrastructure so you can do more things with the data. So computing horsepower. That's been the big shift in the last 10 years, be able to compute a lot more stuff faster on more data.
And then more sources, is that likely to increase or sort of reduce whatever the inherent bias is of the data?
It's an interesting question. I'm agnostic on whether or not it incorporates more or less bias because it all depends on the sources of the data. It could, you think intuitively that it should reduce the bias of the data, but again, it depends on the sources. If the sources are biased, if they're either redundant or if they're biased, we're having this conversation. If you're doing linguistic kinds of models about word usage, if you go back 500 years and look at word usage, it's going to be inherently biased to people who actually wrote. And people who were oral only, we don't have any of that data. So it's biased, and it's always going to be biased no matter how many additional sources, no matter how many different books we find or notes or letters, it's still going to be biased in the same kind of way. So more data doesn't necessarily help. The dangerous thing about more data, though, when I'm in a joking mood, I'll say this. The biggest value of big data is it makes p-values smaller. So everything gets more significant, right? And that's the danger. Just because you have more data doesn't mean it could be statistically significant. The statistical significance is lower, but the operational significance may not change at all, which is a different question, how useful the model is. So more data is good. I like more data, but it doesn't necessarily help with more information to tell you that more interesting things about what problems you're trying to solve.
So we hear that machine learning is going to eliminate, and AI is going to eliminate a lot of jobs. It was interesting that you said only one book has been written that you're familiar with on data preparation. Mm-hmm. It seems like, and if you look a couple of weeks ago in the New York Times, they're talking about a huge influx of jobs which have to do with cleaning the data, because everybody, I think, is starting to realize that if you don't have clean data going in, then you have sort of garbage in, garbage out.
Yep.
But what do you see in terms of career opportunities, and then also whether, on net, this stuff is going to increase the population of the workforce or decrease it?
I think that the data engineer, the ones who are tasked with cleaning up the data, and by cleaning, I mean more than just fixing data problems. I also mean combining data sources, combining data, creating features, all the things you do to the data before you actually build the predictive models. That's going to increase as we have more sources of data, and it's going to get harder. Because when I look at streaming data, IoT data is fantastic. But if you're trying to combine IoT data with more static data, I mean, you've got tall, skinny data, like with millisecond, nanosecond granularity, And you don't care about that kind of granularity. So you've got to bundle it up, aggregate it up to a different level of aggregation to combine with other data sources. That takes a lot of effort. So I think data engineering jobs are going to increase significantly because we are just collecting more data.
Okay. Will you do me a favor? Would you just explain again Simpson's paradox, just sort of briefly?
Okay, so Simpson's paradox, the paradox is this. You could have a trend. You could look at all your data. So let's say, think in terms of the Excel spreadsheet. You're in one column of the data, and you're comparing it to some outcome. And you could look at what the correlation is, for example. And it could be positively correlated. But if you separate the data into two subgroups, like by gender is one of the ones, it could be that it's negatively correlated for both of the subgroups. And so the example, the Wikipedia page that I could put up later for you, but you can just search Simpson's paradox and look at the Wikipedia page. It gives one of these, it's just fascinating how this can happen. Examples of the gender bias at UC Berkeley. So there are 6 departments, and women were accepted at lower rates overall. If you just did the aggregate statistic, women were accepted at lower rates. When you looked at sub-departments, most of them, I think 4 of the 6 departments, women were accepted at higher rates, not lower rates. And the reason is that population sizes for all 6 departments were not the same. So the aggregate statistic is biased by population size of these bigger departments versus smaller departments. So men may have been accepted at an 80% rate in a super small department that had, that mostly men applied to, very few women applied to. And then the big departments that had lower overall acceptance rates, that was driving the women's overall aggregate statistic down. So Simpson's paradox, the paradox is how can subgroups show an opposite trend of the aggregate statistic? And the reason why I like to talk about that is it reminds us how important these interaction effects are in your data. So let me just go one sidetrack. The most popular algorithm employed by data scientists today is linear regression. And that's just the reality of it. Second most popular is logistic regression. These are linear models. These are main effect models. So it's one column, one variable added to another variable, weighted average with all these variables. There's no interaction effects there. So that would find this one trend. The only way you would uncover these contrarian trends is to have interaction effects. So whenever I build a logistic regression model, a linear regression model, I always, and I do mean always, try to identify interaction terms to make the linear models better.
All right, let's open it up for any questions that anybody has in the audience. Anybody raise your hand? Let's do somebody in the back first. We have a ringer in the front, so we're going to wait for a minute.
So for unsupervised learning, sometimes it's hard to find the metrics. So do you have any recommended metrics for unsupervised learning? And how should we find the metrics for unsupervised learning?
Yeah, that's a really good question. So unsupervised learning, so you don't have that target variable. All you're trying to find are how far apart, typically the algorithms work by finding how far apart data points are. And most often, like the classic k-means clustering, uses Euclidean distance, which is that squared error metric. So the first thing I would say with any unsupervised method, pay attention to how you normalize your data. So every variable that's feeding into the k-means cluster model needs to be normalized by scale. So they need to have the same min-max or the same general range. So people usually use z-scoring or min-max normalization to put everything on the same scale. The other problem, though, is this. I mean, data scientists and data miners and the like, we throw any data into the problem. You got the data? Let's try it. Let's see what happens. One of the things that happens, you've got categorical variables. And those categorical variables, like low, medium, high, get thrown into your k-means model. Those are encoded as zeros and ones, right? And those zeros and ones are then used, and we're computing Euclidean distances on 0, 1 variables, which means the distance is either the minimum, 0, or the maximum, 1 squared. Categorical variables will always dominate k-means models, always, because of that max distance. A continuous variable, if it's normally distributed, you don't get many things at the extremes. So that standard deviation is going to be like 0.3, 0.4. But the standard deviation for you, and compute the standard deviation of that 0-1 distribution, it'll be really big, which means it's going to dominate. So the other thing I do is I scale my 0-1 dummy variables to like 0.3, 0.7, so they don't dominate the models. But that's not the question you asked. The question you asked is what metric do you use? What I usually do is you build the k-means model the way it is, and then superimpose something the business is interested in. So let's say you build a k-means clustering model with 8 clusters. Then I may superimpose what revenue was generated from this pattern in the last 6 months, or what's the fraud rate for this kind of pattern, or whatever metric of data you have available to you, and then you can score each cluster with that additional value if you have got that kind of data available to you to try to interpret the clusters better. So that's one thing I do. The other thing I'll do to interpret k-means clusters is I'll build a decision tree to predict the cluster label. Because what's the problem with unsupervised learning? The problem is this. You don't have a target variable, and it's just computing distances. It's hard to interpret exactly why this cluster formed. Once you have the labels, you build a decision tree, and it'll give you a rule to tell you what formed this cluster. If this and this and this were true, you landed in this cluster. And that will help the business stakeholders understand why that cluster formed.
Okay, so while we're getting you a mic up here, we have one over here. Thanks, Krish.
Yeah.
Also, the lesson there was feel free to answer the answer you want to give first, and then the questions.
Could you speak to the educational background and skills that people in analytics teams, BI teams, data engineer, and eventually data scientists, right? I always see doctors that are the real data scientists building these models. So I'm curious about the education background and skills, and it seems like a lot of math and physics people do this. So that's just my experience.
No, it is true.
Krish,
And
bring that up here.
I actually I've gotten into a lot of debates about this because I'm kind of I wouldn't quite put myself into the citizen data science camp, which you may have heard about, that anybody could be a data scientist. So I'm not quite there. But I don't think you need a PhD to do good data science. I don't think you need a master's to do good data science. Now, I have a master's. I don't have a PhD, which actually worked against me as a consultant, because the PhD, the first thing it gives to you is your ticket of entry, because people see if you got a PhD, you must be smart. And if you don't have a PhD, we don't know. So you have to prove yourself. So without that kind of degree as a consultant, it takes a little more effort to overcome that. I think the most important characteristic of a data scientist is intellectual curiosity, not math. And so I call this the Freakonomic mindset. So if you've ever read the book Freakonomics, and if you haven't, it's really easy to read. It's fascinating. But it's asking good questions, loving the data, like just asking the question why. Because here's the thing, a statistician builds models, or they define a model, and then the data tells you whether that hypothesis is accepted or rejected. So the model is king. With data science, the data is king. We're taking whatever data is there, and we're just doing stuff with it. The most important question for data scientists to ask about a model is why. Why did it predict these things well and these things not well? Why did it miss these obvious cases? What's not in the data that's obvious to me that's the algorithm is not picking up on? So that kind of idea is very helpful. Now, that stated, understanding the math is tremendously helpful to try to pick apart why algorithms fail. And we could go through a lot of reasons why algorithms fail, and a lot of them are tied to the mathematics behind how the algorithms are created. I've already banged on linear regression. Squares of errors, outliers kill linear regression models. Sometimes, actually, they help the regression model, but mostly they hurt them. Decision trees are hurt by high cardinality categorical variables. You've got levels, like 1,000 levels, and you just throw them into a tree, and obviously it overfits based upon that. So things like that happen. Understanding the math will help you understand that. But I think the more important thing to understand is loving data and loving to dig into data and pick apart data. I think that's more important. Okay. But that's one reason why engineering is so good. Engineers are always thinking about why does this work, why doesn't it not work? And they're very good at uncovering those ideas.
Great. All right, last question.
Yeah, and I'm going to use my opportunity to ask questions that's going to probably help students. So many of our students, including many universities, are getting offers for data scientist positions at startups. And regardless of whether the startup is going to succeed or not, what kind of support should they be looking for, or what kind of criteria should they be looking for in startups so that they enjoy what they really want to do and they succeed in their jobs? Like, should they be looking for a senior person, whether the senior person is available or not? What kind of criteria would you recommend to look for in the startups?
Yeah, one thing.
So just start with the question of whether or not, that one of the first 5 or 10 employees of any startup should be a data scientist, because you may not have the people there who even have an appreciation for the domain expertise. So you have to wonder whether the person's going to be sitting there twiddling their thumbs.
So when I talk about the three-legged stool, I meant that literally. So with Smarter HQ, the domain expert, Angel, was the first guy. I was the second one. Our first hire was a database guy. So we had all 3 legs of the stool when we started. And so a data scientist I don't think should be the first hire. If you're new to the company, and if you have an undergraduate degree in AI, depending on your ability to handle uncertainty and a lot of questions about how to proceed, you may want to first go to a company that has somebody who can mentor you.
More structure.
More structure, somebody who you communicate well with. Remember, when you're interviewing for a company, it's not just you who's being interviewed. You're interviewing them. And you want whoever you're reporting to be able to communicate well with you and be able to explain what's going on with the company so that you can grow and flourish as well. So I think getting that kind of support for a startup company would be very valuable.
All right, great. So just before we wrap up, I want to remind you that there's a video kiosk in the back. Anybody who wants to take a minute to sort of record a reaction to Dean's talk, we won't share it with Dean, but just so we'll know. But Chris will be manning that machine in the back. And I just want to say thank you for coming and for a very enjoyable and sort of informative talk. And let's give him a hand. Thank you.